Everyone, I am Carlo Macaspag
And I am Angelo Panlaqui.
and we will discuss on adsorption equilibrium of methane, carbon dioxide, and nitrogen on zeolite 13X at high pressures. A study conducted by Simone, Cavinate,
Carlos A. Grande.
and Alirio E. Rodrigues. Abstract. High-pressure adsorption of methane, carbon dioxide, and nitrogen on zeolite 13X was measured in the pressure range 0 to 5 megapascals at 298, 308, and 223 Kelvin and fitted with the Toth and multi-site Lambert models.
Isosteric heats of adsorption were 12.8, 15.3, and 37.2 kilojoules per mole for nitrogen, methane, and carbon dioxide respectively.
The preferential adsorption capacity of carbon dioxide on zeolite 13X was much higher than for other gases, indicating that zeolite 13X can be used for methane purification from natural gas or for carbon dioxide sequestration from flue gas.
Introduction. Natural gas as a fuel is advantageous from an environmental point of view. By using natural gas as a vehicular fuel, reductions in carbon monoxide, carbon dioxide, and sulfur dioxide are 97, 24, and 90% respectively. Natural gas supplies one-fourth of the energy needed in the world's homes, businesses, vehicles, industries, and power plants, and the sum of the natural gas is expected to grow by 50% over the next 20 years.
This is the experimental setup of the closed unit used for gravimetric measurements. The mixture of gas is entered in feed gas inlet. Then, unnecessary gas in the mixture are removed by the purge. Then, the mixture of gas is entered in the oven through valve V2. Take note that V1 and V2 are on-off valves, which regulates the entry of gas in the purge and oven respectively. Inside the oven, the mixture of gas is heated. The oven will regulate and adjust the temperature depending on the temperature employed by the researcher. Then, the heated gas goes to the 3-port valve, then it travels to exhaust through vacuum pump or by the pressure created by the heated gas. The pressure transducer or the pressure sensor will monitor and adjust the pressure depending on the parameter employed by the researcher.
This is the further description of the experimental section. The sample of absorbent is weighed and placed in a basket suspended by a permanent magnet through an electromagnet. The cell in which the basket is housed is then closed, and a vacuum is applied. An analytical balance connected to the magnetic coupling receives the weight values measured inside the cell.
Two Lucas Shevitz pressure transducers were used, one from 0 to 0.1 megapascals with an accuracy of 10 to 5 megapascals, and other from 0 to 25 megapascals with an accuracy of 10 to 3 megapascals, to acquire data at low and high pressures respectively. The activation of the sample was carried out under vacuum at 593 Kelvin overnight. Isotherms were measured at 298, 308, and 323 Kelvin in the range of 0 to 5 megapascals. Adsorption and desorption measurements were performed, and all the isotherms were reversible. The zeolite 13X exudates were kindly provided by CECA France. Some characteristic parameters of the adsorbent are summarized in Table 4. The average crystal size of the sample was obtained by scanning electron microscopy or SEM and is presented in Figure 2. Many observations were performed indicating a very narrow crystal size distribution.
This is the SEM image of the 13X zeolite provided by the CECA France. These are the different characteristic parameters of the zeolite 13X. All gases used were provided by air liquid Portugal, methane N35, carbon dioxide N48, and nitrogen N45. Purities are greater than 99.95, 99.998, and 99.995%.
For the data handling and treatment, we will show several equations that was used by the researcher. As a first step in the description of the adsorption equilibrium, we must distinguish between absolute adsorption and excess adsorption. The difference between them is shown in equation 1. The absolute amount absorbed is equal to the excess amount absorbed plus the density of the gas phase times the volume of adsorbed phase over the mass of the adsorbent times the molecular weight of the gas. The excess adsorption is obtained from the adsorption measurements. In this work, the researcher used a similar protocol reported by Dreisbach and co-workers.
The microbaron signal is equal to the real mass of the gas minus the density of the gas times the volume of the adsorbed phase plus the volume of the solid adsorbed determined by heating.
While the excess amount adsorbed is defined as excess amount adsorbed is equal to the microbalance signal plus the volume of the solid phase times the density of the gas phase over the mass of the adsorbent times the molecular weight of the gas.
The volume of the adsorbed phase is approximately equal to the real mass of the gas all over the density of the adsorbed phase.
The equilibrium data that was obtained from the experiment was fitted using the Thoth model. The equations corresponding to this model are presented by the equations 5, 6, and 7, where the Q sub I and Q sub Mi are the absolute amount absorbed and the maximum amount absorbed of the component I. The standard K sub I is the infinite adsorption constant. Delta H sub I is the isosteric heat of adsorption at zero loading. Ni is the heterogeneity parameter. And A sub I and B sub I are the parameters relating to the thermal variation of the heterogeneity coefficient. The isosteric heat of adsorption decreases with adsorbate loading for N sub I is less than 1.
An alternative model to fit the pure component and binary data was the multi-site Tong model. This model for homogeneous adsorbents, derived by Nita and co-workers using statistical thermodynamic arguments, proved its consistency for treatment of binary equilibrium data. This is presented in equation 8, where AI is the number of neighboring sites occupied by component I and Ki is the equilibrium constant from the Nita model, which has an exponential dependence with temperature, also described by equation 6. In this model, the isosteric heat of adsorption is not a function of adsorbate loading. The saturation capacity of each component is imposed by the thermodynamic constraint AI times QMI is equal to I constant.
To minimize the objective function, the researchers employed square of residuals. Table 1.1 shows the experimental data of methane adsorption equilibrium of zeolite 13x at different temperatures at 298 Kelvin to 308 Kelvin and 323 Kelvin.
While in Table 2, it shows the experimental data of carbon dioxide adsorption equilibrium on zeolite 13x at 298 Kelvin, 308 Kelvin, and 322 Kelvin.
While in Table 3, it shows the experimental data of nitrogen adsorption equilibrium on zeolite 13x at 298 Kelvin, 308 Kelvin, and 323 Kelvin.
We are now down to the results and discussion of the study. Figure 3 is the first sample of the graphical representation of the methane adsorption using the SOR. You can see that as the pressure increases, the amount of gas also increases. The pressure allows the adsorbate particles in the site of the adsorbent, thus increasing the amount of gas absorbed.
The adsorption isotherms of methane, carbon dioxide, and nitrogen gas on zeolite 13x at 298, 308, and 323 Kelvin are shown in figures 4, 5, and 6. Solid lines in the figures represents the thought isotherm fitting, while dotted lines represents the multi-site Langmuir fitting. All the isotherms were completely reversible. At all pressures, carbon dioxide was the most adsorbed gas and nitrogen was the less adsorbed gas. The experimental data corrected are shown in tables 1, 2, and 3.
Figure 4 shows the methane adsorption equilibrium on zeolite 13x at 298 Kelvin, 308 Kelvin, and 323 Kelvin. The solid lines represent the thought model, and if you ignore the solid lines, you will find the broken lines which represent the multi-site Langmuir model. You can see a linear relationship between the pressure and the amount of adsorbent at the initial reaction. As the reaction proceeds, the function becomes hyperbolic. Figure 5.
In figure 5, it is the carbon dioxide adsorption equilibrium on zeolite 13x. The box represents the temperature at 298 Kelvin, while the diamond represents the temperature at 308 Kelvin, and the circle represents the temperature at 323 Kelvin. Solid lines represents Thoth model, while dotted lines represents the multi-site Langmuir model. Figure number 6 shows nitrogen adsorption equilibrium on zeolite 13x. Solid lines represent the Thoth model, and the dotted lines represents the multi-site Langmuir model.
As shown in figures 4 to 6, the Thoth model fits the data very well. The parameters of the fitting are reported in table number 5. The low pressure region was amplified to see that the fitting of the Thoth model is also good. A correct fitting of the low pressure range is essential to describe well multi-component data. This is table number 5 and table number 6. A second analysis was performed using the multi-site Langmuir model. These theoretical models offer a direct extension of the multi-component mixture suitable for PSA modeling. The fitting using this model is also shown in figures 3 to 5. That is represented in dotted lines, and the parameters employed are reported in table 6. As the quantity of the fitting is also very good, this model is preferred for adsorber design application. This is table number 6. The variation of the ideal selectivity of carbon dioxide relative to methane and nitrogen is shown in figure number 7. As you can see, as the pressure increases, the selectivity of carbon dioxide and nitrogen becomes low.
The estimation of isosteric heat of adsorption was done with the low pressure points, and the values are shown in figure 8. Note that the values for carbon dioxide as 37.2 kilojoules per mole is very high when compared to the values of the other gases, which is 15.3 and 12.8 kilojoules per mole for methane and nitrogen gas respectively.
Here are the different works cited in the study, and other references include Conclusion. High pressure adsorption equilibrium from gravimetric adsorption experiments for methane, carbon dioxide, and nitrogen were measured at 298, 308, and 323 Kelvin on zeolite 13X. The data were well fitted with the thought model and multi-site Langmuir models.
Isosteric heats of adsorption were 12.8, 15.3, and 37.2 kilojoules per mole for nitrogen, methane, and carbon dioxide respectively, which indicate a very strong adsorption of carbon dioxide. The adsorbent is very selective to carbon dioxide, which makes it a very good candidate for methane purification from natural gas or for carbon dioxide sequestration from flue gas.
And we're done.
Thank you.